Go ahead, Mehmet.
Live streaming hasn't started.
Yes, it has.
Okay.
Yeah, I had a pop-up said it started.
Okay. Well, good evening. I'm Mehmet Ansoy, Vice President of Denver Astronomical Society. This evening, we have a special set of presentations. We have a panel session with 4 PhD students from University of Denver. The panel topic is Bigger and Farther, a brief journey from neighboring binary stars to distant supernovae and unique galaxies. And we will have 4 speakers going one after each other. Rachel Johnson, Chris Pickens, Sabrina Desoto, and Emma Lieb. And we will have questions at the end, so keep your questions till the end. They will introduce themselves so that we save time here. They'll have brief introduction in the beginning of their presentations. So with that, Rachel, please share your screen and start your presentation.
Sorry, can everyone see my screen now?
Yes.
Okay. All right, well, hi everyone. My name is Rachel Johnson. I'm a PhD candidate at the University of Denver. And today I'll be telling you a bit about the spectral polarimetry of Wr binary systems. So as I mentioned, I'm currently a student here at the University of Denver, but my background is actually in environmental science. As an undergraduate, I started doing research with a graduate student in the astronomy department for fun. I developed an interest in exoplanets, and I found a graduate student interested in observing exoplanet transits with the Ritter 1-meter telescope on campus. So I learned how to operate the telescope, observed some transits of HD 189733b, a short period hot Jupiter, and by the end of my undergraduate career, I decided that I would like to continue pursuing my interest in astronomy, but I didn't really have the background needed to successfully apply to any physics and astronomy graduate programs. So I applied and was accepted into DEVELOP, a remote sensing program at NASA Ames Research Center in Mountain View, California. During my time at Ames, I was able to pick up a couple of additional research projects with astronomers in the astrophysics department, one of which I continued well after I returned to Toledo after the program to continue my physics education. I again picked up an additional research project here with an astronomy postdoc and was able to continue observing with the 1-meter telescope until moving to Denver in 2018 to begin my graduate studies under Dr. Hoffman. And now I'm entering my 5th year here. These are just my publications for you if you'd like to reference them later. So there are 2 groups within our larger research group. Those who study supernovae, which Chris and Sabrina will talk to you about, and those who study WR stars, which includes me and very soon also Emma. So WR stars are known for having strong emission lines in their spectra. These emission lines form in their characteristically dense and very rapidly rotating winds. They're classified based on their emission lines present in their spectra, resulting in 3 main categories: WC, WO, and WN. I focus on WN stars, which have nitrogen emission lines. It's also very common that these stars are with some kind of companion. So specifically, I'll be talking to you about Wno binary systems because those are the current focus of my studies. WR binary systems have been theorized to be progenitors of gamma ray burst producing supernovae. Gamma ray bursts are some of the largest explosions in the universe, but it's not really known where that energy originates. Because WR stars, their wind gets very quickly rotating in these systems around 400 to 500 kilometers per hour. It's thought that the high angular momentum developed here could be the source of the gamma ray bursts. So the figure on this slide shows the approximate location of the targets that we'll be looking at today in this talk. So I'm sure we're all familiar with polarization, but I just want to give everyone a quick refresher just in case. So we get polarized light when unpolarized light, which can be oscillating in many directions, is somehow filtered and the subsequent light oscillates along a single plane. So for our purposes, the light from these systems is being polarized from scattering off of electrons in the circumstellar material. The specific technique that our whole group uses is called spectropolarimetry, which just means that we are looking at the polarization of specific wavelengths of light. This is a particularly powerful technique for us because we're able to measure the amount of polarization within individual emission lines. These emission lines arise at different physical locations in the binary systems, and over time, we can see how much an emission line's polarization varies over the course of the orbit. I am personally interested in coupling optical spectropolarimetry and X-ray spectra because X-rays are much higher energy than optical wavelengths. We know that wherever X-rays are emitting from within the systems, there's some kind of high energy phenomena taking place. And these tend to be regions where WR star winds and O star winds are colliding. Wr94 Cygni is considered to be the canonical case of colliding wind WR binaries. It's been really well studied because it's the closest known eclipsing WR binary system and because it has a very short orbital period, around 4 days. So one of Dr. Hoffman's old graduate students, Dr. Jamie Lomax, combined optical spectropolarimetry and X-ray spectra to constrain the parameters of the cavity that you can see in the top two figures within the stellar wind of Wr94 Cygni. And it's the first study of its kind. So this kind of wind cavity forms from the collision between rapidly rotating, very dense WR star winds and the comparatively thin O star companion winds. The collisions are very high energy, and so we can detect them sometimes in X-ray. Because both the optical and X-ray spectra arise at different phases, depicted on the top left here, a more complete view of the geometry of the system can be constructed. As I mentioned earlier, my research is focused on Wno binary systems that could be analogous with Wr94. So Dr. Hoffman has observation time on the 11-meter South African large telescope called SALT. We have about 70 targets in total, all of which are WR stars. Of those, around half are WN subtypes, but only about 10 are confirmed or suspected Wno binary systems. I suspect that a significant part of my dissertation will likely be centered around investigating the polarimetric signatures of WN systems within our larger sample, and then recreating Dr. Lomax's study that I discussed in the previous slide for as many of these as I can. So far, Dr. Hoffman, our collaborators, and I have been awarded telescope time on Chandra and XMM Newton X-ray telescopes. So 4 of our targets have been observed from one of these telescopes within the last year. Of those 4, I want to share the results of 2 of them with you today, Wr97 and Wr71. Wr97 was the only one of these 2 that was shown to have X-ray emission from a colliding wind region. The binary status of Wr71 actually remains unknown. It was suspected to have an O-star companion at one time, but we so far have no results to support that from our observations. So I've included 5 graphs on this slide. The top row contains plots of the continuum polarization for both targets. The continuum is thought to be basically the background from the star itself and not from the stellar wind. So it's kind of the baseline polarization. The middle row depicts the polarization within 3 of the emission lines that Dr. Lomax used in her study of Wr4. And what we see in these is that Wr97's line polarization being much higher than its continuum polarization. And the polarization signatures of those emission lines vary with phase. So coupled with the X-ray emission, as shown in the bottom left panel, the phase-dependent polarization behavior indicates the presence of colliding wind regions. Wr71, on the other hand, does not have strongly polarized lines, and they don't greatly differ from its continuum behavior, which remains relatively constant in phase. On this slide, I've just condensed all of the plots from the previous page into a single figure so we can see it a bit easier. The top 3 lines are the Wr97 emission lines, and the bottom red line represents Wr71 emission lines, and the continuum for both targets is within that range as well, toward the bottom. And then the bottommost panel of the graph is again depicting the X-ray variability of Wr97. And you can see that it is variable with phase. The next step of my analysis of these targets will be to try and replicate their polarization signatures in a model called SLIP. SLIP is a Monte Carlo radiative transfer code created by Dr. Hoffman for supernovae models during her PhD. Since then, some modifications have been made for it to also simulate binary star interactions. So I've included a simple diagram of how it works. Basically, a photon is emitted from the center of a star. That photon interacts and scatters off of electrons within the stellar wind. It's possible that the photon gets absorbed back into the system at this stage, but if it is emitted from the CSM, its outgoing angle is binned, its polarization and flux are binned, and then the cycle repeats for each subsequent photon. And you can do this millions of times. So just the key takeaways from this talk are that WR binaries are massive star systems thought to be the progenitors of gamma ray burst producing supernovae. Combining optical and X-ray analyses of these systems allow us to determine the general geometry of the system and the location of the colliding wind regions, if any, ultimately allowing us to predict how the system might die. So this kind of analysis has so far only been done on one other system, Wr4, by Dr. Jamie Lomax and her collaborators. However, my goal is to recreate her study on multiple other systems with similar spectral parameters. And I've just included a list of the organizations that have supplied me with the data shown in this talk, mixed in with the institutions that employ my collaborators, which I really appreciate. And that concludes my talk. So I will stop screen sharing now so that Chris can begin telling you about his supernovae research.
Thank you, Rachel. Chris?
Hi, can you guys hear me?
Yes.
Okay,
Yes.
great, wonderful. Okay, I'm going to begin. Thank you, Rachel. That was great. Hi, everyone. My name is Chris. I'm a third-year PhD student at the University of Denver, and I'm working with Dr. Jennifer Hoffman, and I work on supernovae. This is an introduction for really Sabrina's talk on spectra and polarized light studies of supernovae. And so let me just give you some background. You can see in this slide here, you can see some images of supernovae. The images you see, they just look like a little hot spot. One of the goals at DU is to be able to look at a tiny little unresolved spot of where a supernova is, say supernova 2013 DF in the upper left-hand corner over here. Be able to look at a dot like that and tell what the shape of the explosion is, even though we don't have image photometry that resolves that actual spot. Also have here just some collaborators along with the project that goes along with this, this talk. I'll talk a little more about that later. So before actually coming to DU, I was actually at the Denver Museum of Nature and Science. I was an educated performer there. I studied, I taught human physiology and space science to young folks that came to visit the museum. But the museum has a program for which middle school and high school students can come in school groups. And they would come see me, and I would take them through galleries and teach them all about their bodies or about space. Before I was actually at the museum, had a long trip to get there, over 20 years, which started out with my education. I got an undergraduate degree in physics at the University of Virginia. Then I went to graduate school at Johns Hopkins University before arriving at DU. While I was at Hopkins, I actually worked at Space Telescope Science Institute, where I was mostly analyzing images of starburst galaxies with the Wide Field Planetary camera on board Hubble Space Telescope. And then for about, from the years 2001 to 2015, I was a middle and high school teacher, where I taught high school physics and calculus and math, and it was a lot of fun. So yeah, I think what I'll do for myself after I finish my PhD is that I'll continue on in the education field. So I'd like to just define a few things for you guys and help set the background for Sabrina's talk. Let's start off with what is a core collapse supernova, which is the type of supernova that both Sabrina and I focus our studies on. So a core collapse supernova, it marks the end of a very massive star in a titanic stellar explosion. Core collapse supernovae typically occur for stars that are at least eight times the mass of the sun. And during the normal stable lifetime phase of these stars, the inward force of gravity, the self-gravity of the star is balanced by the outward thermal pressure that's produced in the core of the star by nuclear fusion, the fusion of hydrogen to helium. As the star matures, the interior actually gets warmer, and it starts to fuse its interior into heavier elements heavier than helium. It goes through successive stages of starting to burn its material into carbon and oxygen out in the outskirts, nickel and iron in the center. Once iron is formed in the center of the star, a catastrophic core instability occurs, wherein the energy required to fuse elements heavier than iron is not available to the star, and then the thermal pressure shuts off and causes core collapse. The core collapse reverses in response to neutron degeneracy pressure, and that sends supersonic shock waves through the star and it blows the star apart. That's a core collapse supernova. Now in this picture, you saw the ejecta, the expanding envelope, was a spherically symmetric bubble of material that comes out of the star during the explosion. But we've come to understand that most core collapse explosions are not spherical, and at least many of them aren't. A really great example of this is Supernova 1987A, which was a core collapse event that happened in the Large Magellanic Cloud, which is a satellite galaxy to the Milky Way. The distance to this event was about 150,000 light years. What you're looking at is Hubble Space Telescope imaging photometry with the Wide Field Planetary Camera and the Advanced Camera for Surveys. And you can see in the time steps in the lower left-hand corner of each picture, you can see how the supernova is evolving over time. One thing I wanted to point out is that you see a dust ring surrounding the explosion itself. This dust ring formed before the detonation itself. It's very typical for very massive stars like these to actually shed a huge amount of material long before they actually explode. An explosion event, you can see, is actually evolving in the center of the ring. It's been interpreted as being a series of bipolar jets of material that seem to expand over time, which raises some really major questions as to why it is that this explosion is asymmetric. In fact, really to get to it, why are core collapse supernovae asymmetric or aspherical? The answer is that we don't really know, but we have some candidate ideas of what that might be. So one possibility is that the explosion mechanism was asymmetric. Another possibility is that perhaps the stellar winds that accompany massive stars, the winds themselves are asymmetric, creating a kind of perhaps an environment where when the star does explode, the evolving explosion then becomes very asymmetric in response to the circumstellar material around the star. Sabrina and I are concerned particularly with the types of supernova explosions where there may have been mass transfer or some kind of envelope, hydrogen envelope stripping in binary star systems prior to detonation. And so in all three of these scenarios, what the work that we do at DU is to try to start off at a much fundamental level to just kind of establish what the basic geometry is of these explosions as a way to kind of get at this question. What complicates studying core collapse supernovae is that they're not created equally. They kind of come in different flavors, come in different types. Now, traditionally, spectral classification, that is to say, trying to categorize a supernova based on their optical spectra, can reveal kind of like sort of different lines in their spectra. What you see here on the left is a graph of the brightness as a function of color or wavelength of the light that we receive from the supernova explosions. You can see that they're kind of broken into 3 different types. There's a color coding to this that shows the presence of different atomic transitions from atoms that are either present in the expanding ejecta or in the circumstellar environment. For example, or a type 2 supernova core collapse event has very strong hydrogen lines that's shown here in orange, in red. Whereas these yellow sort of absorption lines that you see in a type 1b, which are also not so present in the 1cs, that's due to the presence of helium. Sabrina and I have been able to identify helium in the types of supernova that we study. I specifically don't study these types of supernovae. I study a type called a type 2b. To give you a sense of why these remarkable ones have got my attention, I'm going to show you a series of spectra from 3 different supernovae that are classified as 2b. This is supernova 1993J, this is 2011 DH, and 2016 GKG. The color coding is corresponding again, as you can see that. If you look from top to bottom, this is actually where time is going forward, in the sense that this is early type spectra, this is later type spectra. You can see the number of days after maximum light. You can see almost a kind of continuum in the changes in the optical spectra of these type of supernovae. I like to point out actually a remarkable transition that occurs particularly at the helium and hydrogen line marks that define the type 2b supernovae. You'll notice that over time, you'll notice that the helium lines, the absorption lines, stay present in the spectra, whereas in just a few weeks to just a couple of months, the hydrogen lines actually vanish. This remarkable transition has been interpreted as being a case where these stars may have actually shed their hydrogen envelopes prior to detonation, and in their final explosion, they kind of blow away that last outer sort of layer of hydrogen until it vanishes from the spectra altogether. These oddballs are oddballs. Only about 10% of all core collapse supernovae actually undergo this transition, and those are the types of objects that I'm going to study for my thesis here at DU. This enters into the project that I'm involved in. It's called the Supernova Spectropolarimetry Project, or SNS-POL. In table 1, you see over here are actually the list of all the supernovae that are cataloged as type 2b from the database. And what the database is the largest spectropolarimetry survey to date, with over 100 plus supernovae of various types, of which I only study the type 2b's. And I'll explain what spectropolarimetry is. But the goal of the project is to be able to quantify the degree at which the spectra of these supernova is polarized. Remember, we cannot get an image of these fellows because they're very far away. They're extragalactic supernovae. And so we don't have the capability to get spatially resolved images of what the shapes of these explosions are. What's remarkable about this project is that we can use polarized light. Polarization studies can actually give us some clue as to what the shapes of these explosions are without actually being able to image them. Let me give you an example of this. On the left here, you see is a discovery image of a supernova that I'm studying called Assassin 14AZ. It's in a host galaxy that's almost 40 million light years away. And to my knowledge, both Hubble Space Telescope and, as far as I know, James Webb does not have the imaging capability to be able to resolve this particular supernova into an image that we can study the geometry directly. You see the host galaxy there is just that smudge, and this is a Sloan Digital Sky survey of the supernovae. Now, traditional optical spectra studies that have no polarization data in it might look like something like this, where you might take a spectrum of the supernova at different times in its evolution. Early light type spectra might be the ones at the top, and later type spectra are the ones on the bottom. We tend to mark their number of days as the number of days since maximum light. As in their light curves, they tend to get very, very bright when they explode, and then they tend to kind of get fainter over time. We mark each sort of spectra as a kind of epoch. can mark the changes in the spectra to really try to study the physical changes in the spectra over time. What DU adds to things like this, to studies like this, is polarization data. This is just a reminder on the bottom here that you're looking at the run of wavelengths from 4,000 angstroms to 8,000 angstroms. This is the wavelength of the light, which corresponds on the electromagnetic spectrum as the visible portion or optical portion of the spectrum. What we can add to that data is this types of things that you see here. The funny looking dotted lines that you see here that are really hard to see are the original spectra that I just showed you. And superimposed on top of them is a kind of rigid looking blocky, I don't know, looks like a city skyline type of set of graphs, right? Looks like a city skyline. That's polarization data. Like this is what is measuring what is the degree at which the light is polarized as a function of wavelength. Specifically, this is the percentage of the light in the background that you see at each graph. What percentage of that light is actually polarized? And again, we can actually mark the changes in the polarization spectra and figure out what that might mean. Let's just talk a little bit more about where this comes from. So light from supernova gets polarized, and the process at which it's done that happens is called electron scattering, as Rachel had mentioned. So the idea is that imagine that black dot in the center there is the actual supernova, and the red little envelope you see there is the expanding ejector from the explosion. The light from the explosion is highly ionizing radiation, and as it filters through the envelope of the supernova, the light can strip atoms of their electrons, essentially ionizing the atoms within the envelope. So if you look at ordinary gas, either in atomic or molecular form on Earth, in the lower left-hand corner, you can see in this little diagram, you see here's the atomic nucleus, and that little dot there is the electrons that are in orbit around the nucleus of the atoms. These are neutral atoms. But when you ionize material, you can strip the atoms of the electrons and you have a sea of free electrons that are within the envelope itself. It is this sea of free electrons that actually scatters the light from the supernova and polarizes it. You can see in the lower right-hand corner, unpolarized light, represented by the blue, baby blue cross, strikes at a single electron. Electron re-emits after scattering that light, and oscillation, the plane of oscillation of the electric field vector of that radiation is now in a very well-defined plane. That's what polarized light is. And spectropolarimetry is actually a window into the geometry of supernovae. Let me show you how that works. So this is called polarization by electron scattering. And what started it all was this paper that was published in the Astrophysical Journal in 1982, which showed that if you had a image that was unresolved of a supernova, but you can measure the degree at which the net total polarization of the light is from that supernova, then you have a chance of figuring out what the shape of the expanding envelope is around the star. The idea is that on the left-hand side, you're looking at just one electron scattering event, but within the actual cloud expanding around the star, you'll have multiple scattering events throughout the cloud. You can imagine that each scattering event will create a very specific plane of polarization for the light that emerges after scattering, so the polarized light. This paper was the first to show that if your envelope of the scattering region was perfectly spherical, then all the components of the net polarization from that signal that you would detect from your telescope, which have a polarimeter on there, and again, we don't have a fully resolved image of the supernovae. And so what you are receiving is the net polarization from all the scatterings as integrated over the entire surface of this supernova as projected onto the sky. They showed that if the envelope is perfectly spherical, then all the different vectors in linear polarization called the U and Q Stokes parameters will cancel each other out and you get zero net polarization. However, there's even a very small degree of aspherical structure to the envelope. It slightly deviates from spherical symmetry, then not all of the vectors in the polarization signal will cancel each other out and you'll get a non-zero net polarization. You may not necessarily know the actual geometry specifically, but you'd know if you receive a signal that's non-zero, that is not spherical. And all of this, and trying to do this in practice, there are some complications. On the left here, you're looking at is typical data, what I look at and what Sabrina looks at. of a spectrum that shows the percent polarization or net polarization as a function of velocity. I'll explain that in a moment. The baby blue in the back is the optical spectrum of this supernova. This is again assassin 14AZ. What I've marked here is actually a helium transition that occurs at 5876 angstroms or 587.6 nanometers. This is the rest wavelength of that atomic transition, which is why I marked it as 0 kilometers per second, because this would be the light that this atom would either emit or absorb, so long as it's not moving relative to us. You'll notice that in the spectrum in the blue, there doesn't seem to be any interesting features near helium 15876, but to the left of it, which turns out to be blue words in wavelength of that rest wavelength frequency of rest wavelength. You'll notice that there's a kind of dip in the spectrum. That's an absorption line. That absorption line occurs precisely at the same place where we see a non-zero % polarization in our spectra, in our polarization spectra. The physical picture that emerges when we look at images like this, when we look at spectra like this, is that what we're seeing is the supernova is along the line of sight between us and the cloud and the supernova. It creates a kind of line of sight. And the idea is that the light from the supernova filters through an ionizing cloud or an ionized cloud, creates a kind of continuum source, which represents the wings of this absorption line up here. The presence of the cloud steals light from the continuum source, making a dip. So we know that absorption line tells us that there's an intervening cloud between us and the supernova hot spot. The fact that it's non-zero polarization tells us that whatever the shape of this region is, it's not spherical, it's some kind of asymmetric scattering region. I cannot stress how powerful this technique is, and that what we've done here in this picture is not only equate the idea that we can measure the speed at which this object is moving towards us, because remember, this is all happening in the supernova wind. And so the reason why this blue shifted or shifted to shorter wavelengths relative to rest wavelengths is because the ejecta is moving relative to us into the continuum. And so that blue shift can be used to actually measure the expansion velocity of the supernova wind. So you need to know the speed of light, the rest wavelength of the transition, and you have to, of course, know the observed wavelength of the transition. You can calculate how fast the cloud is moving towards you. We estimate the speed of the cloud is approaching us at about 9,000 kilometers per second. That's a scattering region that's asymmetric. So we've been able to connect kinematics, motion in the cloud, with geometry. It's a really powerful technique. So when I think about SNS pole, I kind of think of it as kind of a paradigm shift in the way we think about supernovae. The idea is that we've come to realize over the last couple of decades that from both imaging and from both spectropolarimetry studies, a vast majority of core collapse events are not spherically symmetric. Maybe most of them aren't. And that changes our picture as to how they may work, to thinking about them as being something where the asymmetry may either be somehow connected to the explosion mechanism or something in the environment or both. And so NSN Pole is a first large survey for supernova shapes. And when I tend to ask myself the question of what can we learn regarding how they work by studying their explosion geometry. There are three things to take away from all of this. It's kind of like, what is NSPS Pole? And it's a survey of supernova geometry evolution. The how is that we use spectropolarimetry to uncover the shapes of supernova ejecta in their circumstellar environment. And the why we do it, why we're interested, why I'm interested in, is that I'm very interested in knowing what the mass loss and explosion mechanisms are like for massive stars. When I was at Space Telescope, I studied how massive stars formed. And so part of the excitement of me being part of the DU program is that now I come to study not just how they go from learning how they're born, but now learn a little bit more about how they perish. And in all the studies that I've ever read about massive stars, one of the most key important parameters in understanding how they evolve is the mass loss rate. And so with the type 2b supernova that I'm studying, where they show a very marked change in how much they change the presence of their outer envelopes, that is to say that they seem to have, they're losing that last layer of hydrogen, tells me something about, or at least gives me an opportunity to learn more about mass loss in these systems. Okay, that's all I wanted to say. So thank you, DS. Here's my email, and please email me if you have any questions.
Thank you, Chris.
Yeah.
Thank you, Chris. Sabrina, please proceed.
Sure thing. That was an excellent introduction, Chris. Thank you very much for that. Okay, so moving right along, I'm Sabrina Desoto. I might have met a few of you before in a presentation I did here or perhaps at the board meeting. So a little bit about me. I'm born and raised in Colorado. I then left Colorado for a liberal arts and sciences school in British Columbia, Canada. There I got the opportunity to shape my own education, wherein instead of getting a bachelor's of science in physics, I just got to pose a question and try to answer that question the best I could. So I made it as broad as I could to answer as much or to learn as much physics as I could. And I tried to decide, where does physics become undefined? So that led me through my undergraduate degree. And then afterwards, I came back home to Colorado and eventually joined this group here at the University of Denver. I worked previously in my first year with Dr. Robert Stencil. You all might be familiar with him as previously running the Chamberlain Observatory. And the work I did with him was studying light pollution. Once he retired, I then joined Jennifer Hoffman's group, which brings me to our presentation today. All right, so as Chris alluded to, I study core collapse supernovae, as does he. And the topic of my presentation today is on one particular supernova, supernova 2012 AU. This faint, here, let's get a laser pointer going. This faint glowing ball right off the center of this galaxy here. And so I'm going to talk about more specifically, how do we do the research on these supernovae? So what I'm going to show here is a time lapse of 6 different epochs of data that we have on the supernova. As Chris described before, these are Spectropolarimetry Epochs. So we have the flux in the light blue in the background. And again, that blocky black line is the total percent polarization. And we're watching how it changes over time. Specifically, I've marked a couple of the rest wavelengths for some of these lines in the spectra. And we can see that there's non-zero polarization. So we know that it's aspherical and that it is changing over time, that amount of polarization. So let's break this down a little bit and just look at one epoch of data, one day that we particularly viewed the supernova. And this was 26 days after its maximum brightness, epoch 2 in our data set. And so here now I have marked the rest wavelength, again, for helium 5876 line, a very common element to see in this type of supernovae. And I have marked the plus or minus 15,000 kilometers per second velocity shift from that rest wavelength, as Chris kind of noted in one of his slides there. So within this region, we can pick out a few features. We see that there is a peak in the relative flux right at that rest wavelength. There is a dip, blue shifted, or towards the left of the rest wavelength, towards the shorter wavelengths, bluer in the spectra from that peak. And that along with that dip in the flux, there is also a dip in the polarization from which it starts to climb into its peak polarization afterwards. So another way to look at this would be to break up this total polarization that we see here in the black line into its component vectors and put that on a Q and U diagram. What is Q and U? Just a reminder. So that total polarization is this main vector here, and its components can be divvied into the Q in one direction and the U in the opposing direction. So if we break down that total polarization into its component vectors, and we plot each of those points between the negative 15,000 kilometers per second to the positive 15,000 kilometers per second, this is the trend in the data that we see for this helium-1 line. And it's very interesting because it does not trend along one single linearity in space, but rather creates this nice loop-looking feature. So what does this mean? What is so interesting about a loop, and what can we learn from this? Well, so another way to look at this, as Chris noted, is to really break down what is happening at each of these velocities. So now I have the blue side from the rest wavelength, which is marked by this X, is plotted here for velocities going 0 to negative 15,000 kilometers per second. And the red side from 0 to positive 15,000 kilometers per second. And we can see that this loop really is a function of the bluer end of line area that we're seeing there, which means that as the ejecta is traveling, as we get towards those negative velocities, we get a change in the polarization direction, and we get these differences in the polarization, which are telling us about the structure of the supernovae. So more so, as we're looking at these negative velocities, a negative velocity could be interpreted as an ejecta coming towards us, or as us looking further and further into the ejecta and seeing that there is non-zero polarization. So there is some sort of perhaps a clumpy structure in there creating this increase and this difference in the vectors of polarization. And so, as I said, this was just the one epoch of data, that day 26. We had 6 epochs for this supernova. This scale actually is no longer in percentage, it's fractional, so do ignore that. You'd have to multiply it by 100 to get true percents. But what I'm showing here is that, again, we play this game to see how it's changing and developing over time. So that in the first epoch, we see that there's only a small divergence from linearity, and then we get this nice loop feature. That loop kind of starts to collapse down on itself. And throughout the whole time, it's kind of following the same trend in that same quadrant in space until we get to these later epochs when it completely flips, which means that the polarization itself is changing direction. It's changing how it's polarized until we get to this day all the way out in 295 days since its maximum brightness. And we have this flip in the opposite direction from this vector here down where it's there. So what does this tell us really about the shape? How do we go from this again to the shape? If we're looking further into the supernovae, how do we know what we're seeing about the shape? Which brings us to the modeling side for the supernovae. As Rachel introduced, we use a code called the Supernova Line Polarization Code, known as SLIP. And from the supernova side, what we can do with SLIP is we can create models to try to match the polarization levels that we are seeing in our data. And when we're creating these models, we're keeping these parameters, or we're changing these parameters of shape and density and the angle at which we're viewing the system itself. And so here I have 2 plots of just examples of a model that I've been running. And so these would be like a slice in a single plane of view, maybe like the XY plane. And so we can vary the geometry and size of the emitting region. That's these solid blue blocks here. Is it going to emit bipolar, or is it going to emit already in an ellipsoid shape? We can vary the density of the light of the material that it's going to travel through. How does that affect the light being polarized? And finally, what I'm most interested in is we can add perhaps clumps to the ejecta, things that'll absorb the light in different ways. And how do those differences in the size and the shape of these clumps change that polarization level? So again, if I'm trying to match some polarization levels that I see here, I'm trying a whole bunch of different combinations of these things to try to recreate the structures that we see within the data we've observed. And so to date, there are 4 type 1b supernovae that have been studied using spectral polarimetry, and we can compare what we're seeing to what those other published showed. And sure enough, they also see loops in their QU plane. And so if we can do this comparison to say that these types of supernovae all exhibit these loops, and we can quantify these types of polarization, and then we can go one step further to say that this polarization is maybe caused by this clump in the ejecta, then we can start to say something about these types of supernovae as a whole. And again, really pounding down the importance of SNS pole is the vast amount of data that we have to add to this study. So these are all of the type 1b and 1c supernovae that I will be studying throughout my PhD here, starting at the top with 2012 AUEC. And these are all of the number of observations we have on each of those supernovae. So with all these new supernovae to add to the system and all of the observations that we have on them, we are going to more than triple the amount of type 1b and 1c supernovae that we've studied and published anything on today. So the takeaway points for us then are that the polarization data shows that supernova 2012 AU is in fact an asymmetric explosion. Observations combined with slit models will help us to suggest preferred geometries causing this asymmetry in the explosion, and that other type 1b and c supernovae exhibit similar line polarization features. So it's really important for us to make an understanding of how all of these types are related and what are the similarities that we're seeing through all of them. So thank you very much for that. And we're going to switch gears a little bit here onto Emma Lieb, our newest member of our graduate group.
Thank you, Sabrina.
Yeah. Okay. Hi, everyone. So my name's Emma Lieb. I'm going to talk today about bar-driven leading spiral arms in isolated disk galaxies. This is a research based off of paper that I wrote with my co-authors, Angela Collier and Anne-Marie Madigan, which we published last fall. So as okay, my slide's not moving forward. Okay, sorry. As Sabrina said, I'm starting at DU this year, so I'm a first-year graduate student. I'm originally from Northern New Jersey, but I did my bachelor's degree in Boulder, at CU Boulder. So I'm going to be studying Wno binary stars, which is what Rachel talked to you about, but I haven't started that yet. So this research is on some work that I did in undergrad. So let's get into it. I'm just going to front load with the definitions of some of our key terms. Leading versus trailing arms, we're going to talk about in the next slide. A gigayear, which is the time scale that we work on in this study, is 1 billion years. An n-body simulation is a computer model of a system of particles under the influence of gravity. As Rachel and Sabrina talked about, models are really important in astronomy because we can't actually take these systems into a lab and like figure out what they're doing. So an n-body simulation, similar to other models, is where we just put different particles in, give it a specific amount of mass, tell it to, give it, Newton's laws and let it go over time. And this is, this is how a lot of astronomy is done. So spiral density waves, according to us, are the arms of spiral galaxies, which is, what the Milky Way is, for example. A galactic bar is an overdensity of mass at the center of some spiral galaxies. And the big one here is a co-rotation resonance. So this is where the overall rotation of a galaxy matches the rotation of that galactic bar. It creates a resonance there, and the radius at which that resonance occurs is actually really important to the dynamics of spiral arms. So what is a trailing arm? Basically, when we look out in the universe and we look at all the grand spiral galaxies that we see, most of them, pretty much all of them, have trailing arms. This means that when we look at the arm, the tip of the spiral arm points in the opposite direction of the overall rotation of the galaxy. So these white arrows indicate that this is the direction the whole galaxy is rotating, and the arms trail behind that rotation. Like I said, almost all galaxies that we see in the universe follow this trend. There are, however, a couple examples in nature of leading spiral arms. This is the opposite of trailing, where the tip of the spiral arm points in the direction of the overall rotation of the galaxy. Again, the white arrow indicates the overall rotation of the galaxy, and this red arrow is the direction of our spiral arm. Here I've pictured NGC 4622. This is a Hubble image. This is one of the very few cases where leading arms have been discovered. So that'll tell us, this is actually a really rare phenomena. Back in the 50s, the question was posed, can leading arms even happen? Is that even possible? They did a really big survey. That was Pasha et al. 1956, and they found no leading spiral arms back then. So they said, nope, leading spiral arms aren't possible. Let's close this question. Let's stop looking at it theoretically. Me and my co-authors decided, you know what, let's see, maybe they are possible. Let's create an n-body simulation. Let's run it through time and see if we can actually get leading spiral arms. So I'm going to, without further ado, show you a movie of our n-body simulation. So here she is. This is the disk. These are all of our stellar particles that are moving through time. This time scale is gigayears, as I said. Right around 5 gigayears here, we're going to start to see really strong trailing arms. This is what we normally see. As we get towards 6 gigayears, the arms, the lighter portion of these arms are actually going to lead in front of the bar. So here we go. We can see that the arms are actually leading now. They're in front of the rotation of this bar. These spiral arms are long-lived. They actually stay leading for 3 full gigayears, up until roughly 8 gigayears. Eventually, we're actually going to see these arms entirely decouple from the bar. That isn't really the focus of this research, but it's interesting to see as you get to really large galactic times. This is, what some galaxies probably do. So I'm just going to let it finish out. And here our arms are decoupled. They're not actually rotating with the bar anymore. Pretty neat. Okay, so there we go. Okay, so spiral density waves. In our simulation, we have a disk, which is the stellar particles that I showed, and within around that disk is a dark matter halo. So all spiral galaxies in the universe have a dark matter halo around it. What's unique about our simulation, our galaxy, is that the halo rotates counter to the disk rotation. So basically the disk is rotating in one direction and the halo is rotating in the opposite direction. That's important because this co-rotation resonance that I was talking about, where that happens is equal to where the pattern rotation of the bar matches the pattern rotation of the disk. Usually in nature, this co-rotation resonance happens at a radius that's very, very close to the bar, like right around here where my cursor is. The bar is always generating these spiral density waves. It creates these 4 waves all the time. The thing about it, though, the reason we only see certain arms is that only specific density waves are allowed to thrive. This is the case without getting into a lot of math. Basically, long arms are positive arms. They get amplified at this resonance, and short arms get absorbed. They get damped away by something called Landau dampening. So basically, inside the co-rotation resonance, our leading arm is allowed to thrive. It gets amplified, and outside the co-rotation radius, the trailing arms are allowed to thrive. They get amplified there. What's dynamically happening is that the stars in the galaxy inside the co-rotation radius are actually orbiting faster than the bar. So that makes sense. That's why they populate this leading arm. Outside the co-rotation resonance, those stars are actually orbiting slower than the bar, so they obviously populate this trailing arm. They trail behind the bar. All right, so I'm also just going to show really quickly a plot of these radii. This is the x-axis is time here. The y-axis is radius. We'll focus on our RCR. This is our co-rotation resonance, the radius of that co-rotation resonance. This black line indicates where our leading spiral arms actually start. We can see that by the time they start, the co-rotation radius has already been moving out, and after they form, the co-rotation radius just moves way far out, 30 kiloparsecs. It moves so far out that this is where our leading spiral arms are allowed to thrive. It's why it doesn't mean that there isn't a spiral density wave that's trailing. It just means that it's not getting populated, so we can't see it. Okay, to further prove my analysis here, we're going to look at the angular momentum flow of this system. Right off the bat, I've excluded our units because they're not important. Let's just remember that a loss of angular momentum is in blue and a gain of angular momentum is in red. First off, we see a sink of angular momentum to the inner dark matter halo. This is basically where we know that our arms are going to are forming. This is also where something called a buckling happens. I'm showing here a side view of our galaxy. We can actually see that the galaxy buckles. It creates a this is where our arms have formed. So once this buckling occurs, we actually get our leading spiral arms beginning after this black line again. During the strong leading spiral arms, we see another massive sink into the dark matter halo. This, we theorize, is due to something that we're calling a dark matter wake or a dark matter bar. I'm showing here a map, a density map of our dark matter particles. So the black line here indicates our stellar bar, and we can see a really strong perpendicular dark matter wake forming perpendicularly to this stellar bar. This dark matter wake is creating so much torque on the stellar bar that this is what's actually allowed it to slow down. The bar slowed down, it moved our co-rotation radius out, and it allowed our leading spiral arms to thrive. Just very much at the end, we see an increase of angular momentum into the outer parts of the disk. This is where that decoupling of the arms that I was telling you about happens, and our galaxy dies after about 10 gigayears. So the major takeaway here, something is torquing the galactic bar. For us, that was a counter-rotating dark matter halo, but we theorize that anything that significantly torques the bar could allow the co-rotation radius to slow down. This could be something like a significantly massive satellite galaxy. Anything that torques the bar will slow it down. When the bar slows down, our co-rotation radius moves really far out, and then inside there, we can see leading spiral arms thrive. So this is important because we've reopened a question that was closed quite a long time ago, and it proves that leading spiral arms are possible, so we should do more surveys and try to find them. Thanks so much. If you guys want to stay in touch, you can use that QR code. If you want, it has my contact. I can also put my email in the chat. Thanks so much.
Thank you very much, Emma. Thank you very much to all of you. So we had 4 excellent presentations here. Now we are open to questions. I see one question here from Greg. Greg, why don't you start?
Hey guys, thanks for the great presentations. Chris, I've got probably a really basic question for you. The Hubble images that showed the evolution of that supernova didn't show any distortion or that to the outer ring. Do you know why?
It's a good question, and I'm not sure. But when I think about fluid dynamics, right, I would imagine that, well, let me see if I can go back to the, are you referring to Supernova 1987A, is that correct?
The one you had the Hubble images of.
Yeah, okay, yep. So yeah, in that image, here we go. So that the geometry here, it almost looks as if it's like everything's in the plane, but in one of my slides, it shows that there's the spatial relationship between the explosion and the ring are different. So let's imagine that you're looking, if you're looking at the ring straight on, like face on, the ring is here and there's the explosion. You first see that the explosion itself is tipped by 15 degrees laterally. And then if you're looking, if you can see this explosion from the side, then what you would find is the circumstellar ring itself is not quite in the, like, so the ring itself is like, here's the edge on part of it. And the explosion is happening at like out of the plane of the ring itself. You can see it's tipped at 45 degrees. So in terms of, if I think about fluid dynamics, and I can't see how the center will actually exert any ram pressure in the direction of the ring itself to kind of distort it, right? But please don't quote me on that. These are optical images, and so just keep in mind that I don't see the full geometry of the entire circumstellar material here. It could be more stuff here that you can see at other wavelengths. So my guess would be I wouldn't want to try to guess at that, but that's a very good question. Thank you.
Oh, thank you.
Dina had a question earlier. Dina?
Yes, I did. My question would probably be for Chris, pardon me. Is it reasonable to think that there is no such thing as a perfectly symmetrical supernova explosion?
That's a good question. So I try to look for, I've been reading a lot of papers on like what types of spectropolarimetry signatures that come from different types. Certainly of the core collapse supernovae, I almost rarely hear of one being perfectly spherical, but I have read some papers where another type, which is not a core collapse supernova, it's called a type 1A. That mechanism involves a binary star system where you have an evolved star that's now a white dwarf. It's in orbit around a massive star, and then the white dwarf steals material from that star in mass transfer. And once the white dwarf reaches a critical mass called the Chandrasekhar mass, it explodes. I've seen, oddly enough, and almost counterintuitively, because when I think about systems like that geometrically, I feel like there's a very particular axis to it, and it doesn't feel like that would necessarily be symmetric. But I've read papers where there have been very little spectropolarimetric signature to them. They have very low net polarization. But I would never really. The problem, what I'm learning is that supernova are probably just as varied as people on planet Earth, but they're almost individuals. And so I'd rather not say for sure with great confidence again.
Okay.
It just seems to me like there's so much mass there that the likelihood of it all being in absolute perfect distribution would be nearly impossible.
Almost lucky. Maybe.
Okay, Ron is asking everyone, but maybe Chris, you can answer this. What is meant by percent polarization?
Yes, percent polarization. Sorry, I didn't clarify that. So we receive a total light as a function of wavelength, like an integrated brightness of the supernova in the spectrum. And so a spectra.
And let me expand on that question just a little bit. I come from the world of RF or radio frequency engineering, where I deal with generally linear polarization, vertical or horizontal polarity, or circular polarization. But I hear the term percentage polarization in the presentations talking about spectropolarimetry, and I'm wondering exactly how that ties into the world of polarization as I understand it.
Okay, so the first question would be, so the percent polarization is just, so you'll notice that in this picture, these two graphs you see here, the one in the background is like the total intensity as a function of wavelength, the brightness of the supernova as a function of wavelength. That would include.
So you can think of that background as being magnitude versus frequency, or magnitude versus wavelength.
Yep, absolutely.
Okay.
And so what the percent polarization is the percentage of that light in the background that you see in this graph that's polarized. You'll notice that it's very small. 2%, 4% of it at these particular wavelengths. Spectral
Okay,
polarimetry.
when you say that the percentage of the background light that's polarized, we can assume that that background light has random polarization, and that you're pulling out a measure of some percentage that has a characteristic polarization of where the electric field vectors are aligned in a certain direction.
Yeah, in the
is there a
net.
preferential direction?
There is. In fact, what I don't show you here is that not only do we get a magnitude of the net polarization that we receive from the supernova light, but we also have a direction in which is projected onto the sky. And so, Sabrina mentioned this a little bit. She mentioned the U and Q Stokes parameters for linear polarization. You can think of those as components of that net polarization that we receive from the supernova as projected onto the sky in some direction. So it has a very well-defined magnitude and orientation in space. Unfortunately, it's all projected against the sky. So it doesn't, trying to get three-dimensional information from that, you can't get directly from observations. You have to go and use models to be able to create synthetic polarization spectra for supernova envelopes of various geometries whose polarization source is primarily electron scattering. And so,
Okay.
yeah.
That clarified it. Thank you. And those UQ diagrams reminded me of in phase and quadrature, or IQ diagrams that I deal with in the world of data and RF.
Okay, next question. Maybe I'll direct that to Rachel by Nikhil, asking how an observing person, how can we help you in your research?
Yeah, so if I may clarify, go ahead.
Go ahead.
No, continue.
Yeah, so if I may clarify on that, so I'm primarily a telescope observer. I use a couple of telescopes, and I would, if I want to help you, which I would love to, how would a person like me be able to help you? Thank you.
This is a really good question. I'm trying to think of a way. I've been staring at it for a while, like since you've posted it.
Yeah, and if it sounds silly, forget it. Just
no, it's a great question. So I'm not sure about the supernovae that Chris and Sabrina look at, but all of my targets are in the southern hemisphere, so we won't be able to see any of them here. So
binary stars are available in the northern hemisphere as well.
Yeah, the WR binary stars are also in the northern hemisphere.
Yeah, yeah. Right.
I don't know how visible they are though.
Right.
That is the only thing.
Maybe with data mining, if that is possible, because data mining can also be done, right, on archived images or something similar.
What were you saying, Sabrina?
Just thinking of more generally, I think as a group have found when we give presentations like this, and more specifically when we give presentations to even like conferences or explain to other astronomers what we do, polarimetry is kind of a scary topic. So even if you just start to talk about polarimetry amongst yourselves and amongst the participants at DAS, and Mehmet mentioned before we did these presentations that you guys knew what polarized light was, which is honestly even impressive for us going to other conferences. It's usually a very scary topic. So if we can just like kind of start talking about it more casually in terms of being a resource for knowledge, that kind of might help not only our research group, but other people to be inspired to do polarimetry research. Because I think what Rachel's getting at is that even though there are targets in the northern hemisphere, not a lot of polarimeters are necessarily put onto telescopes, or it's not necessarily valued as a field in astronomy as much as it should be at this point.
Okay, I have a question for Emma. You did mention the dark matter a bit. What is the relationship between dark matter and spiral galaxies, in the sense whether they make a difference for leading versus trailing. Does dark matter matter if it is leading or trailing?
So in our simulation, yes, the dark matter halo is entirely what allows us to see leading spiral arms. It's much trickier when you're talking about actually observing this in nature. I don't actually, it may be possible, but I can't think of any studies off the top of my head that have actually been able to resolve what direction the halo is rotating with respect to the disk. So in our sense, yes, it's very important. And we theorize that it probably is something that happens out in nature. And that is, a reason why we could possibly see more leading spiral arms. The difficulty with observing leading spiral arms is that it requires a very specific observing geometry. So we need to see the galaxy face on enough to tell that it's a spiral galaxy, and we need to see it edge on enough to tell which direction it's actually rotating. You need to get a Doppler shift in order to tell which direction it's actually rotating. So if you have for example, if you look at a galaxy that's completely flat face onto us, we can't actually tell if those arms are leading or trailing because we can't see which direction it's actually rotating without a Doppler shift.
Can the spiral galaxy hold together without dark matter?
I would say no. Most massive galaxies, I'm pretty sure all massive galaxies except the super old ones, have a very significant dark matter halo. So I think that, yeah, the dark matter halo is intrinsic to these grand design spiral galaxies.
Okay. There is a question here from Douglas. I was going to ask how you can even tell what rotation the dark matter has, but I guess the answer is we can't really. Is that true?
Yeah. There have been a lot of theoretical studies done on how what the distribution of rotation of dark matter halos are. But in terms of observing it, since we can't observe dark matter yet, hopefully maybe someday we will, we can't actually tell which direction they're rotating. So this is why models are really, really useful. They give us actual ways to poke the physics and figure out whether or not these things are even mathematically possible. So.
Okay. Well, I have one final question for Sabrina about your space initiative, the Students Physics and Astronomy Club for Everyone. Can you tell this group what this initiative is all about and especially the rationale for it?
Absolutely, I'd love to. Thanks for taking some time to discuss it again. So the four of us, Emma, Chris, Rachel, and myself, have decided to do some outreach of our own, which is coming in the form of starting an after-school club for a local middle school, Prairie Middle School in Aurora. We chose this location because it is a predominantly Hispanic and minority middle school that is underfunded. And we would like to give these students some opportunity to explore space and physics, and to do so in a way that they don't feel they can fail at. They don't feel like at this age, if they're bad at math, if they're bad at science, that they don't belong in those fields. We want to really encourage this group of students to pursue their interests in space, in physics, if they have any at all. And we want to give them the opportunity to do so in a fun manner while not putting additional stress on the school itself. So the club will begin probably in about a month. Their school starts in about a week, and we're giving the teachers and the students a little bit of time to settle and passing out invites to this club, which will be completely free to attend for the students, which is where you guys all came in. I gave a presentation about a month ago to your board, and you guys have all been very supportive of us so far. which we're really grateful for. And we are just very excited to start this and to interact with these students.
Okay, great. Yeah, we very much appreciate the initiative, and we will be supportive of the initiative. So, are there any last minute questions? There are several remarks, but I don't see any other questions. Are there any questions? Yes, Digby, please. Unmute Digby.
Yeah, my question is, for us astronomers that are using relatively small telescopes, say 10 to 20 inches in aperture, are there any objects that we might observe where we might actually see some supernova, or actually where we might see distortion of the galactic bar?
Who should we address that to?
That's to the entire group there.
Yeah, okay. Sabrina, you want to take that?
Honestly, no. Somebody
No,
else might have
okay.
a better response than I do, because I really don't know. I'm sorry.
Wasn't it Emma that was?
Emma, do you think you have an answer?
Yeah, so for for amateur telescopes, absolutely there are a lot of targets that are possible. There are some galactic targets. Unfortunately, by eye, the galactic targets are not going to be super spectacular. You're going to want to do like longer exposures and take a look at images, maybe stacking those images in order to get like really nice defined spiral arms and bars. I don't know anything about distortions of bars or seeing, you can't see any sort of evolution of galaxies on human time scales. But I do believe that there are supernovae remnants that are definitely visible, definitely able to be observed. But again, not a lot of these deep sky objects, I'm sure, as you guys all know, are like super easy to see just like through your eyepiece. It works really well if you take longer exposures and look at images of these things. But they're definitely possible to do with amateur-sized telescopes.
Digby, is that good enough?
What are the objects where we might point our telescopes and do some imaging?
So one of them would be the Crab Nebula, that is a supernova remnant. Huh?
M1.
Yep. And I mean, it's really hard off the top of my head for me to think of good galaxies where you can actually see the spiral arms. I can try to find a list for you though, if you guys wanted me to add a link to that. I know that I'm sure you guys have all looked at Andromeda. That takes kind of a lot of hours of get like really nice clear arms. So yeah, I'm sorry, I don't know off the top of my head, but definitely I can provide with some resources.
Awesome, thank you.
So there are some messier galaxies that you can easily see the spiral arms in a 12-inch to 20-inch telescope. I mean, pretty much. Yeah.
Go ahead, Nikhil.
Yeah, that is what I was saying, that depending on the telescope, you can see spiral arms for all the major messier galaxies, even some of the NGC ones in the northern hemisphere.
Okay.
Right, but they're talking about seeing distortion in the bars.
No, I don't think that is possible with our.
No, they're talking
Probably
about needing
not,
to
yeah.
take many images and stack them, and about, that'll take hours and hours of imaging to see the distortion in the bars.
Okay, any other questions?
I put a comment in the chat window, but an electronic integrating eyepiece that automatically stacks images can let you see that on an external monitor. I've got a monochrome one. We used to have one at Chamberlain. It may still be there in the equipment cabinet. And the nice thing is it does 256 image captures, stacks them, and then you put it on the video monitor, and you can, or up to 256 images. And I've seen spiral arms in the Whirlpool galaxy in a 5-inch refractor with that setup. And I've also seen the central star in the Ring Nebula. So that technique works well. So just if you are stuck like most of us are with small to medium or moderate aperture telescopes less than say 20 inches or so, that type of technology can really be a big help.
Dr. Hoffman, why don't you voice what you put on the chat line?
Sure. Can you hear me? I'm not sure I've got a good mic.
Yes, we
here.
can hear
Okay.
you.
Yeah, I put a web link in the chat that is a website that keeps track of the currently active supernovae. So of course, supernovae are going off all the time in external galaxies, and they brighten and fade. And so the site is really useful. I've used it for my own observing runs to figure out like what is actually observable at any given time. And if you go there, they are sorting the supernova by current magnitude. So you want to look at the top of the list for the brightest supernovae. And then the brightest one right now is 12.1 magnitudes. So, you know, if you have a big enough telescope, and especially I love Ron's suggestion of the integrating IPs, that gives you some idea of what the supernovae are that are currently available, and you can click on these and get a little finding chart and a little image of it. So those of you with larger apertures and darker skies may want to get that.
Where's that link, Doctor?
That's in the chat. rochesterastronomy.org/supernova.
See the chat window, Digby?
Yeah.
Okay. I have a question. Somebody may have said this, I may have missed it, but who was the person who came up with the idea of detecting the dark matter based on whether the spiral arms led the galaxy direction of turn or followed it? Does anybody have any idea who came up with that concept in the first place?
Well, the question of leading arms versus trailing arms was posed in the 50s, sort of outside the idea of dark matter at all. It was later that I think it was Vera Rubin who figured out that there's a significant amount of dark matter in galaxies. That we figured that out by looking at the velocity of stars in these galaxies, and I'm sure, yeah, you guys know that story. But yeah, we actually the cases of nature that were seen, I think as far back as maybe the 70s and 80s. Basically, those are leading because of satellite galaxies that are orbiting those spirals, and that's what's creating the dynamics that allows for the leading spiral arms. So yeah, the halo argument is not necessarily tied to the original question of whether or not arms could lead.
Okay. I just that whole thing just blew my mind. Sorry.
No worries. If you guys, I guess I can link to my paper, and I have a couple other presentations I gave on it that are longer than this one. If you guys wanted to learn more, I can link to that.
Well, actually, I would like all four of you sending your presentations, copies of your presentations to me so that we make it available to the members, in addition to the live streaming of on our YouTube channel.
That would be wonderful.
Any other questions? It's getting late.
Yes.
I don't see anybody else. Let me check the other screen. Yes, Digby, you have another question, or you haven't lowered your hand?
Yeah, I don't think he's ever put it down.
Okay. Well, thank you very much, all four of you. You did a great job. I think you can make Dr. Hoffman proud, or you have made her proud. And we very much appreciate a very informative session, excellent presentations, and we wish you success, and we wish you completing your program successfully as quickly as possible, I guess. Okay, thank you.
Thank you.
Thank you so much. Thank you.
I'm going to stop the live stream.